What I wanted to talk about today is primarily 3D rigid body kinematics. This has to do with rotation matrices and all of that. And the common way that we write rotation matrices is in terms of Euler angles. There's other ways. Another one we'll talk about is the principal axis and angle of rotation. There's other things called quaternions that we won't get into in this class, but I'm gonna talk about that. And why does this come up? It's because this is how you describe the rotation of a rigid body. So rigid body dynamics those are the equations of motion which give us the angular velocity of the body fixed frame with respect to the inertial frame as a function of time. So we typically have some ordinary differential equations for the components of the angular velocity, and we can solve those. But to know the current configuration of the body, and by configuration, I mean orientation or attitude. Right, I'll use my phone as an example. Here's my phone. If I get my phone spinning or something, there's some angular velocity vector and it'll be evolving. But how do I describe the current orientation of my phone compared to some, say, reference frame? So if I have an inertial frame and a body fixed frame, I want to describe how that body fixed frame moves with respect to the inertial frame. So what is the current orientation of the phone? And that can be described with a rotation matrix. So we will describe that with a rotation matrix. And it'll be a rotation matrix. Usually it's written as going from the inertial frame to the body fixed frame. And so this will be, in general, like a 3x3 matrix in 3D. And we won't talk about it today, probably next week. There's a relationship between the angular velocity and the rotation matrix, so that you can go from one to the other. And we're not going to say what it is today, because 3D rigid body kinematics is difficult on its own. And maybe it's good to have a, no, we'll get to the picture later. This matrix is usually, we say, parameterized in terms of angles of rotation about different axes, and those are called orientation angles or Euler angles. Okay, so it's easiest to start out doing this in 2D, because rotations, we just have a 2D world, are easier. But in general, we'll be talking about orientation in 3D and Euler angles. But let's start in 2D. So if I have here's a inertial frame, right, E1, E2, is my inertial frame. And I've got a body in 2D something like that. And I've got a body fixed frame, right? The only way to describe the orientation of a body is to first consider that you have a frame attached to the body. So there's a frame, we'll call it the B frame. It's attached to the body. If you want, there's some third direction popping out of the screen. Third direction doesn't really matter here, but we want to describe the orientation of the B1 and B2 directions with respect to the E1 and E2 directions. So even if you're thinking of the origin of the inertial frame as being down here in the lower left, you just sort of superimpose what the directions are. And then we would say, okay, all we need is one angle theta, right? And that describes how the B frame is rotated with respect to the I frame. So in this case, what do we need? We need a single angle theta to describe the orientation of the body fixed frame. B frame. That means we're trying to just describe how the B directions, in this case, B1 and B2, with respect to the inertial directions. E1, E2. So how do we do this? Well, we've used that writing things in terms of a table. So we could do that again. If you remember this kind of table thing. I'll write a table. Got the E directions up here, the B directions here. And then in each of the boxes, I'm writing the dot product of those two unit vectors. And the dot product is typically going to give a sine or cosine. So E1 dotted with B1 is cosine theta. B1 dotted with E2 is sine theta, and so on. And then we can write this, another way to kind of write this would be in terms of a matrix format. So we would write B1, B2 as if it was a column vector equals a matrix times E1, E2, where what is this rotation matrix here? It's literally just take this group of sines and cosines there. That's our matrix. So this equals cosine theta, sine theta, negative sine theta, cosine theta, E1, E2. So in this case, we might say that theta is an Euler angle. It doesn't really have a name because the Euler angles were really made for doing rotations in 3D, and this is just 2D. So theta is our Euler angle. Like it doesn't have some name like Yaw Pitch and Roll or anything. It's just the angle between these two. We sometimes compactly write this as B equals C, this is a matrix, times E. This is just a compact way of writing the relationship between the frames, where by B, we mean this is just shorthand for kind of the collection of unit vectors. And this generalizes to 3D. So instead of right now, we've got a collection of just 2 unit vectors. We could do this as a collection of 3. Okay, you might ask, okay, what if I wanted to go from one frame to the other? And I guess there's something to notice here, right? The notation here of this C matrix, we've got the B up here, it's a superscript up on the left, and it's on the same side as the B unit vectors. And then the I frame unit vectors are over here. Like maybe we'll do that. Yeah, I think you get it. So this is the transformation. Also known as rotation. It's a transformation matrix, or equivalently a rotation matrix for this case, from the frame I, basically the unit vectors, the basis vectors, to frame B, basis vectors or unit vectors. It's an orthogonal matrix. So in terms of mathematically, what is it? It's an orthogonal matrix, which means that its inverse is its transpose. And so its inverse would be, so CIB inverse is the same as going from the B unit vectors to the inertial frame unit vectors. So we could write that as in this notation, and that will be the same because we have a orthogonal matrix. It's the same as this transpose. Okay. Now, what if I wrote this, I included these unit vectors pointing in the third dimension. They're kind of boring, but let's say we included them. So we treat this as an actual rotation in 3D. What would the 3D rotation matrix be? So if we treat this as a rotation in 3D, then we would have the rotation matrix is, now we would have a 3x3 matrix, but all of the important business would be in a 2x2 block. So this upper block here, and then there'd be a number 1, and then everything else would be 0. Right, because why is that? Because E3 equals B3. There's no relationship with using sines and cosines. So maybe you recognize this from some other class. We'll use the notation capital R 3 theta. This means, the notation here means this is a counterclockwise rotation. Let's look up here. What does it mean? Yeah. It's a counterclockwise rotation about the number 3 axis. So the basis vectors are rotated by a counterclockwise rotation through an angle theta about the number 3 axis. In fact, let me just, right, because we'll use this later on. So the notation Ri alpha is a counterclockwise rotation about the axis I through an angle alpha. Okay. All right, so this, and I guess one of the main things here, one key thing is we're talking about how the basis vectors are related to each other. The way basis vectors are related to each other is different than if I had a vector as seen in one frame. What does it look like in another frame? So let me say more about what I mean by that. So this matrix describes how the basis vectors are related. We need to do a little more reasoning to figure out how a vector in one frame appears in another frame. What do I mean by that? So say, phrase it this way, how do body fixed vectors transform? So if I've got here I'm just sketching the body, and that body fixed frame. And suppose I want to track this point P, this corner of the body. And I'll use the middle of my body as the origin. So let's write this vector, which is R P with respect to O. R P with respect to O. If we were to write that in the body fixed frame, it would have, say, a Cartesian component, YB and XB. So this looks like XB, YB. And what does this vector look like when I then transform into the inertial frame? So this might be important for doing a simulation or animation. I want to know how this point P, actually all points along the body, how are they moving in the inertial space? So let me sketch what I'm talking about. As this thing is rotating, so it's got some rotation, the point P now is here. The vector, I want to write what this vector looks like, RPO, but as seen with respect to the inertial frame basis vectors. So I've got my basis vector B1, B2, and then I've got the inertial frame, E1, inertial directions, I should say, E1 and E2. So clearly, right, this is X sub XE and YE. I'm writing the components of this. It's the same vector, but seen in a different frame. So what is that? Let's write it, R, P, O. With respect to the I frame, this is XE, YE. With respect to the inertial frame, equals, and we write this. It is, you'll notice I've written, it's ICB, right? And this thing, like we said up above, is CIB transpose. So you have to be careful if you're looking at how do the basis vectors transform and how do the body fixed vectors transform, because there's this difference of a transpose that you need to be aware of, okay? So now let's try doing all of this stuff, writing the rotation matrices in 3D. And if you were looking to read about this in the book, it's in section 10.4. So now, instead of just like a square, I've got some solid block, and I've got some body fixed vectors, B1, B2, B3. And now I want to know, how do the basis vectors transform into the inertial frame? Basically, how do we describe the orientation of the body? And it's how do we describe the B1, B2, and B3 directions with respect to E1, E2, and E3? So I'm going to try to now draw the box at some kind of weird angle. And here's the inertial directions. And then the body fixed directions will be at some, orientation compared to that. B1, B2, B3. So we're asking the question, how do we describe orientations in 3D? And it's the same procedure. We want some matrix, a rotation matrix that relates the B directions, B1, B2, B3, the body fixed directions, to some inertially fixed directions. And we can do that. And there's multiple ways, but we often use, we will use here, Euler Angles. And what do the Euler Angles do? The Euler Angles describe this matrix that describes the orientation of the B unit vectors with respect to the E unit vectors, which is it's going to be a 3x3 matrix. The Euler Angles describe this through a series, actually a sequence of 3 rotations. And we'll get into that. Let's see, which one do I want to do here? So there's actually 12 different sets of Euler angles. One that I'll describe is called 3, 2, 3. But then there are others, like the usual yaw, pitch, and roll. This 3, 2, 3 is not yaw, pitch, and roll. And I'll explain what this notation is. And why am I even doing 3, 3, 2, 3? This is because the book uses it. So if you wanted to follow along. And it's also used in for analysis of gyroscope problems or gyroscopic problems, and also orbital mechanics. If you want to, yeah, it gets used in orbital mechanics. So it's kind of, this is significant, and let's describe what it is. So like I said, you go through a sequence of rotations. It's good to have a picture. So let me find that picture. Here it is. And this is from the book. So let's explain what's going on here. This is some body. I don't know why they chose a kind of ellipsoid shape. I would have chosen the box thing. But we first do a rotation. So you first consider a rotation about the number 3 axis. So if you have a body, like my phone, I don't know which one we've chosen as the number 3 axis, but you rotate first through that number 3 axis about an angle, or through an angle psi. Okay, and this takes us from the inertial frame to what we'll call the A frame. A is just some kind of intermediate frame. So A and C are intermediate. Finally, we want to get to the B frame. So the first rotation is about the number 3 axis. And it takes us to, we're going from the inertial frame unit vectors, which we described with these E things, and the A frame unit vectors. So we did a rotation about the number 3 axis, which means, so you could write this either as a table or equivalently as a matrix. We're doing a rotation. It's a clockwise, so you use the right-hand rule. Your thumb points in the direction of the axis you're rotating about, and then your fingers are curling in the direction of the angle. So in this case, my thumb is pointing in that number 3 direction, the E3, which is the same as the A3 axis, and then my fingers are curling. So this is, in the notation we had above, it's just R3 psi. So this is going to be cosine psi, sine psi, 0, negative sine psi, cosine psi. Everywhere else is zeros, and then we have a 1. So this is the matrix that takes us from the I frame unit vectors to the A frame unit vectors. And in this case, it's just the same as R3 psi. Counterclockwise rotation through the angle psi about the 3rd axis. And I guess we could also remind ourselves what this is giving. The A basis equals C I A, and then the E unit vectors. Okay, so that's the first rotation. That's this rotation up here. It takes us from the I frame to the A frame. So now we're in this kind of intermediate frame. We want to go from the A frame to the C frame. And this is a rotation about, to get a different rotation, we can't rotate about the number 3 direction again, because that would just be like continuing the former rotation. So we have to pick either the number 1 direction or the number 2 direction. In this case, we've chosen, we're going to rotate about the number 2 direction. That's over here, and we'll rotate through an angle theta. So this is rotating about the number 2 axis, which is a new direction compared to the former number 2 direction. The former number 2 direction was over here, but now it's been switched to being this direction. So we're rotating, again, right-hand rule, my thumb points in this number 2 direction, my finger curls in the direction that theta is going. This one is not an easy one to write down. but we will be using the same notation. This would be, instead of R3 psi, this will be R2 theta. And this would be describing how the C directions equals this rotation from the A to the C unit vectors A. Again, we make a table, but now the A unit vectors are along the top here. And then this intermediate frame, call it the C frame. Okay, and then the number 2 direction stays the same. So there's just a 1 and a bunch of zeros. And this is what the matrix looks like. So this is the rotation from the A basis vectors to the C basis vectors, and it's also in our notation. It's R2, rotation about the number 2 axis through an angle theta. Okay, so that takes us, that's the second in the sequence of 3 rotations. The last rotation takes us from this intermediate C frame to the actual body fixed frame. And this will be a, so the first rotation was about 3. The second rotation had to be around 1 or 2. It couldn't be 3. We chose 2. Now this third rotation can't be about the number 2 direction. It could be around the number 1 direction or the number 3 direction. We're choosing in this convention to rotate about the number 3 direction again. But it's, you've got to note the number 3 direction is now in a different direction. But we'll be rotating, we'll call this rotation angle phi. So this is now a rotation about, let's say it's a new direction and the new 3 axis. Okay. Over here, this is also rotation about the new number 2 axis. And just like before, we're going to write the B unit vectors are related by a rotation matrix from the C unit vectors to the B unit vectors times the C unit vectors. All right, make our table where now the C unit vectors are along the top and the B unit vectors are down here. And this will be, we could just sort of copy what we had up here for a rotation about the number 3 direction. Just change the angle now. This is cosine phi, sine phi, negative sine phi, cosine phi, 0, 0, 1, 0, 0. Easy peasy lemon squeezy. Okay, this is CCB, and this is using our notation of these R matrices. It's rotation about the number 3 axis through an angle phi. Yay. Now what? Oh, because ultimately, what did we want? We want the B unit vectors related to the some matrix that takes us from the I to the B. So the E unit vectors. And what is that? Well, it's this sum of notations. B, let's write what we have. B equals R3 phi of C. So I'm just going from up here on the right-hand side. Okay, but what is C? This is R3 phi C can be written in terms of the A unit vectors as R2 theta A. But then finally, R3 phi R2 theta. The A unit vectors can be written as R3 psi of E. Okay, so that means that this matrix multiplication is the rotation matrix that we're looking for. Okay, so we can write this matrix as it's a function of three angles, psi, theta, phi, and it equals R3 phi R2 theta R3 psi. So this is the utility of the Euler angles, is that you break down the orientation into a sequence of three pure rotations about axes. This particular one is the 3-2-3 convention, and there are other conventions. So if you actually work out this matrix multiplication, you get something that's not terribly pretty, but I will show you, and you don't have to copy this. It is not pretty. There it is. So each of these components is what you would obtain if you were to work out the matrix multiplication. So this is CIB for the 3-2-3 Euler angles. All right. And I guess it's worth noting each of these components is what? So if I have each of these components of this matrix, so let's say the ijth component is equal to bi dotted with ej. It's the dot product of those two unit vectors. And if I wanted to go the reverse, so from the B frame to the I frame, that equals C I B transpose. And how might that be useful? That would be useful if I'm trying to describe, I'll do something similar to what I had up above. If I'm trying to describe where a corner of my a corner of this box, what it is. This is RPO. Then I've got my unit vectors in the body fixed frame, B1, B2, B3. If I were to look at this as it's kind of rotating through space, and I want to describe where is that, what is that vector? What are the components of that vector as seen in an E frame, the inertial frame? Well, just like before, but now with three components, this thing would be, let's call it XB, YB, ZB. That's how it looks in the body fixed frame. But now when we go to the inertial frame, this will have components. Let's call them XE, YE, ZE. And this will equal CB to I. See, B to I is the I to B transpose. So it's the transpose of this matrix we've written here in this table times the matrix XB, YB, CB. And now I've used the example of I'm trying to track the corner. You could use this relationship for any vector that's in the body fixed frame to transform what are its components in the inertial frame. Any vector, not just a vector that's some point on the body, but any vector. And if you want to follow along in the book, this is equation 10.38. Okay. So how many Euler angle conventions are there? There are many. They are legion. Well, okay, you have a choice. N1 is the number of choices for the first rotation. And you could choose any of the three directions, 1, 2, or 3. So that is a 3 times how many choices do you have for the second rotation? Well, you can't choose the same one as you used before. So 1 drops out and you only have a choice of 2. And then what about the third rotation? Well, you can't use the one you used for the second rotation. You got to use one of the other 2. So this is also a 2. So this means 3 times 2 times 2. There are 12 choices of Euler angle convention. The one that we just did up above is called the 3-2-3. A popular choice is the one that's used in aerospace. And it's actually 3, 2, 1. And the angles, I don't know if there's any standardization in what we call those angles, but let's say the first rotation was through an angle psi. We actually give that one a name, yaw. And then the second rotation is through an angle theta, which we call pitch. And the third rotation, let's just call it phi, but that's roll. And that's why these are sometimes called yaw, pitch, and roll. I don't know why this name is attached. Maybe these people think they invented it. Tate, sometimes called the Tate-Bryan convention. There's and I'll give you this table. There's a whole table of all of the Euler angles. This is an appendix C from a different book, Schaub and Junkins, but it gives the various Euler angle transformations. Again, it says here there are 12. They just write the matrix as C, but this is the same as what we've been writing, BCI. Okay. They also call it the direction cosine matrix. And just to write it more compactly, they write S for sine and C for cosine. And so this shows the matrices for all the conventions, 1, 2, 1, 1, 2, 3, 1, 3, 1. If you were to look at, what did we just do? 3, 2, 3? 3, 2, 3. So what I've written here, this is just, it's the same. They're just writing it in terms of the angle theta 1 is the first rotation, then theta 2 is the second rotation, theta 3 is the third rotation. So all of the conventions are here. You might say, well, why would I choose anything other than say yaw, pitch, and roll? It depends on the problem. For some problems, it's more convenient to use a certain set. So for like gyroscopic and orbital mechanics situations, the 3, 2, 3 actually makes more sense. But 3, 2, 1 is convenient. It's useful for not just aerospace, but it's useful in vehicle dynamics. Because if you think of a vehicle and you're just looking at kind of small rotations in one of the 3 directions, you want 3, 2, 1. And I will show, for some reason, I have a picture of a spaceship. If any of you have seen the old Battlestar Galactica from the 80s, this looks a lot like one of those ships. I think this is also from Schaub and Junkins. So if we were to write spaceship is a vehicle, right? So if we were to write the Yaw Pitch and Roll matrix, it says we write it as 3, 2, 1, but remember the order that we do the matrix multiplication is reversed. So we do R3. It'd be first a rotation about the number 3 direction through an angle psi, and then R2 rotation about the new number 2 direction through an angle theta, and then R1 rotation about the new number 1 direction through an angle phi. And if you want to see what the matrix multiplication looks like, look at page 433 of the book. I'm not going to write a bunch of sines and cosines. And like I said, this one's convenient because the angles have common names. There's we've got yaw, we've got pitch, and we've got roll. And so you need to be careful. Okay, what is a positive roll? A positive roll, my thumb points in the number 1 direction, my fingers curl. So that means if I'm in the vehicle, this would be a turn to the right. This defines positive roll. Positive pitch, my thumb pointing in the B2 direction. Positive pitch means pitching up. What about yaw? What's positive yaw? My thumb pointing down. Positive yaw means turning to the right. So there we go. All right. There's another way to describe rotations. And it's called the principal axis and angle of rotation. So let's say something about that. The principal axis and angle of rotation. This is due to something called Euler's rotation theorem. This Euler, he did a lot. And the idea is if you have a rotation, any rotation can be written as, so you could either write it in this Euler angle convention of 3 rotations about pure axes, or you could think of it as there's one principal direction, a principal axis, and you're only doing a rotation about that. So any rotation matrix can be written this way. And this is something that Euler proved in his rotation theorem. So the idea is if you have your 2 frames initially lined up, so let me just do the 2 frames initially lined up. So I've got my E1 and the B1, E2 and B2, E3, B3. If they're initially lined up, then, and the B unit vectors are rotated with respect to the E unit vector. So let me write the E unit vectors as just sort of staying still. The B unit vectors are in some other place and in 3D. You could view the relationship, you could view this matrix that takes us from one frame to the other in terms of there's a principal axis. So we'll give this a hat. It's a unit direction. And there's a rotation. And it's usually written as phi. And that describes the rotation from one frame to the other. So this could be, I'll just write it in words, equals a rotation through an angle phi about the axis a hat. Phi is the angle of the rotation, and a hat is called and it is a unit vector. It's called the principal axis of the rotation. So what does this mean? Like in terms of my, I've got a GoPro here. Check it out. This is kind of like a block. For my GoPro, if I want to go from this sort of reference configuration to any other configuration, that can always be written as a rotation about a single axis with a certain angle, no matter what the initial and final orientation are. And that's what Euler proved. So you could view that we've got this 3x3 matrix. The 3x3 matrix can equivalently be written in terms of 3 Euler angles. Or you could write it in terms of a principal axis and angle. And then you can even go between Euler angles and the principal axis and angle. So there's all these equivalent ways to write a rotation. Okay. Let me just write for you how you actually write the C matrix in terms of the A matrix. So because it's just cumbersome to put the CIB, I guess we could keep it. I'm just going to say write C as CIB. Okay, so the relationship is, later we can prove it, but we need some more machinery related to the kinematic ODE. But for now, I'm just going to give this to you. C equals E to the negative phi, and then this is A cross product, the A cross product matrix. In fact, maybe I won't write it that way. I'll write it as A tilde. A tilde. A tilde is the same as the A cross product matrix. And hopefully you remember what the cross product matrix is. Right. The cross product matrix means we take, so the A as a unit vector has components A1, A2, A3. So when we write the A cross product matrix, I guess this was A, not as a vector, but had a little hat. We just sort of apply the usual approach of going from A to the A cross product. So this is negative A3, A2, negative A1, and remember there's zeros along the diagonal. This is a skew symmetric matrix. And this is A3, negative A2, A1. So this is a 3x3 matrix. So I've written C equals the exponential of phi times a 3x3 matrix. And if you haven't seen the exponential of a matrix, here's a little mathematical note. So if I write E to the A, where A is a matrix, the matrix exponential is defined in terms of what looks like a Taylor series expansion for exponential, but you put the matrix there instead of a scalar. So this would be the identity matrix plus A plus 1 over 2 factorial A squared, so on. Okay. So this is the relationship kind of written in its most elegant form. But let's work it out. If you write it out, this is, let's take that matrix exponential. This is going to be the 3×3 unit vector plus the angle phi times negative a tilde plus 1/2 factorial phi squared a tilde squared, and so on. If you work that out from the Taylor series expansion for the exponential, this actually, you can collect terms and you get something that looks pretty nice. You get the 3×3 matrix times cosine phi minus a tilde sine phi. So that's a 3×3 matrix times sine phi plus a hat transpose 1 minus cosine phi. And remember what this is. This is just a way of writing that matrix. So there's a nice closed form expression for it. This was found by a mathematician named Rodriguez. So this is called Rodriguez formula. So what does this represent? This represents going from the axis and angle to the rotation matrix. But we can also do the inverse. So if you have a rotation matrix, you can go to the axis and angle. And this is the formula. The angle is inverse cosine of 1/2 times the trace of your matrix C. Remember what the trace is? It's just the sum of the diagonal elements minus 1. That's the angle. The unit vector, the principal axis, A1, A2, A3, is, you need to actually calculate this angle first, because then you'll do 1/2 times sine of that angle. And then this is a matrix written using components. So this is C23 minus C32. That's the 2,3 component of that matrix C. Right, and then C31 minus C13, C12 minus C21. So there we go. You might wonder, why do we not write this A matrix? Why aren't we saying this is the components in either the B frame or the I frame? It's because this is the one direction, which is actually the same in both frames. So that's kind of interesting. A1, A2, A3 in the B frame is exactly the same as A1, A2, A3. The components are exactly the same. So we usually just sort of just drop the little subscript and say A1, A2, A3. It kind of makes sense. It's the one direction that you're rotating about, so nothing will change along that direction. Okay. You're going to need to use this phi for one of the homework problems, and I'll give you a hint. Right, so I think this is for, that's for the folded triangle. The last part of that is asking you something related to the rotation and finding the principal direction. And there's actually multiple principal directions. You want to pick the smallest one, right? You could either do a rotation about this direction through a small angle, or through the opposite direction through a large angle. So you should get, this is for homework 3 to D, the angle that you should get, something around 42 degrees. So this is 42.45 degrees. So you can check with that. All right. Sound good? Good. Let me show some videos of rotations because I want to give you an idea. Here's a 3, 2, 3 Euler angle sequence. So I think this is supposed to be some, arbitrary shape. And so the two frames start out the same. We first do a rotation through the number 3 axis. Now we've got a new number 2 axis. We rotate about that. And then the number 3 direction's in a new place. So that's it. So this is kind of slowly showing to show the arbitrary body fixed frame. How can you get there? You can describe it as a rotation about 3 pure axes. So that's the 3, 2, 3 convention. What if we did 3, 1, 3? So this is first, it's 3, 1, 3. So first a rotation about the number 3. And now instead of number 2, we choose this number 1 direction, the x direction. And then finally, we do another rotation about the number 3 direction. Okay, so that's the 3, 2, 3, 3, 1, 3. Here's 3, 2, 1. So here's a jet. We first do yaw, pitch, and roll. So any arbitrary orientation of this airplane can be written as some combination of yaw, pitch, and roll. I like that one because the graphics are cool. Yaw, pitch, roll. So all of these were positive. That's why the yaw was to the right. That's a positive yaw. The pitch was up. So that's a positive pitch. And then the roll was a roll to the right. It's a positive roll. You could do negative angles as well. And so you can achieve any, describe any orientation. If you did want to see the 3, 2, 1 Euler angles, there they are. So I will kind of give a preview. The relationship between the rotation matrix, which I'm writing the rotation matrix as if it's this static thing, but it's actually going to be changing in time to describe how the body is changing its orientation in time. And that is going to come from, be related to the angular velocity. And how do you get the angular velocity? The angular velocity comes from rigid body dynamics. But then how do we go from omega to c? What's that step? Sometimes, right, since we could write this in terms of Euler angles, and let's just say yaw, pitch, and roll. There's a relationship between the rate of change of yaw and pitch and roll. This equals some 3x3 matrix times omega 1, omega 2, omega 3. So once you've solved for, and these are changing in time, maybe we'll just put parentheses t just to remind us, those are changing in time. This thing is called the Rotational Kinematic Ode. And this matrix here that I put a big question mark in, is what I think we'll have to do that next time. But it is a matrix that depends on, it's got some entries. Maybe I'll put little stars. It's got entries, and these entries depend on the Euler angles. So each of these entries it'll be some combination of sines and cosines, right? Each of these entries depends on the Euler angles. So you've got this strange nonlinear ODE to go from the components of the angular velocity as a function of time to how the Euler angles change as a function of time. And then once you have that, you've got your rotation matrix and how that changes as a function of time.